So here we're in section 6.4, and what we're going to see here is we're actually going to graph the sine function and the cosine function. And we're also, later on, we're also going to graph the so-called variance of it. We're going to have a times sine. This little w-like symbol is actually called omega. So we're going to graph a times the sine of omega times x. Omega is really any non-zero number. But as you'll see later on, it's really enough to consider omega being positive. And we'll do the same thing for cosine. A, this number in front, is just a non-zero real number. Okay? So we're going to graph sine and cosine. Now, here, x is actually going to be, it's going to represent an angle in radians. That's our input. You could think of x as an arbitrary real number, but if you went back to the definition of how the trig functions are defined at an angle in radians and at a real number, they're almost identical. So really, it doesn't matter that much. But now, for convenience, let's think of our input as an angle in radians. So we're going to focus on sine of x, okay? Now, when graphing a function, of course, the more numbers from the domain that you use to graph the function, the better your graph's going to look. But for a time consideration, we're only going to focus on certain x values. Now, remember, sine is 2 pi periodic. So it's really enough to know what's happening in any interval of length 2 pi. We're going to focus on this interval from 0 to 2 pi. So once we know how what the sine graph looks like for x in this interval, then we're good. But again, any interval of length 2 pi would work. Now, we're only for now going to look at these x values. Of course, the more x values from this interval that we choose, the better the graph's going to look. But as you'll see, it's really enough to know what's happening here. Okay, then if you were to use how sine of x is defined, you would actually get these values here. So sine of 0 is 0. Remember, x here represents an angle in radians. Sine of pi over 2 is 1, and so on. So we're going to get these x values. Let's see if I can write them in. We're going to have 0, 0. Next, we'll have pi over 2, 1. Okay, we're going to need these points because we're going to plot them. Here we have pi, 0. Here we'll have 3 pi over 2, negative 1. And then at 2 pi, right, again, we'll get 0. Mostly because sine is 2 pi periodic. So we're going to plot these points, and then we're going to sketch a graph of it. Okay, so let's see if I can do that. So again, we're focusing on the interval from 0 to 2 pi. Here, pi, remember, is about 3.14. So we're only going to have an approximation, of course. See if I can make this a little bit nicer. Like so. Okay, now, at 0, sine is 0, right? We have that point. Next, at pi over 2, we're going to get 1. Okay, so let's plot that. At negative pi, we're going to get 0. 3 pi over 2, we get, see if I can make that just a little bit nicer. 3 pi over 2, we'll get negative 1. And at 2 pi, again, we'll get 0. So if you were to connect these dots, so to say, your graph's going to look something like this. And of course, again, the more x values we use, the better the graph would look like. But this is actually what the sine graph looks like. It kind of looks like a wave, so to say. You know, you go up a bit, stop at 1, at this point up here, go down to this point, and then you go back up to the x-axis. But that's what the sine graph looks like on the interval from 0 to 2 pi. That's what the sine graph looks like. So this is what the graph of sine of x looks like on the interval from 0 to 2 pi. That's what our graph of sine of x looks like. This is actually what we call one cycle of the graph of sine of x. This is what one cycle looks like. But now the question is, how would you graph this outside of the interval 0 to 2 pi? You basically just keep repeating the cycles. In other words, you would continue in both directions. So here I reproduce the graph again, and let's say we want to go to the right of 2 pi. Well, again, we're going to follow the same pattern. The cycle is going to repeat. So to the right of 2 pi, the graph is going to rise up until pi over 2 units to the right, you're going to be at 1. And pi over 2 units to the right, you get 5 pi over 2. And then it's going to fall back down to 0 when you get the 3 pi. You know, you add another pi over 2 units. So it's going to fall back down to 0. I don't have enough room to write it, but this here would be pi. And you basically would just keep on going. You keep on repeating the cycles. Likewise, to the left over here, so to the left of 0, it's going to look like the way it does to the left of 2 pi, right? You're going to go down a bit until eventually you'll hit -1 pi over 2 units to the left. So it's kind of hard to see here because I only have so much room. See if I can draw it a little bit better. But that's what would happen. So basically the cycle would keep on going. You know, it would keep on going indefinitely. And again, I do recommend you draw the graph, you know, using Desmos or some other graphing technology that you have, just to see what the entire graph looks like. But again, it's just going to be this pattern, you know, this complete cycle. It's going to continue indefinitely. And here are just some basic properties of the sine function. Some of this we actually have said already, but the domain, right, is the entire real line. You know, we have mentioned it already, that the sine of x is defined for every real number x. And the range is all numbers between -1 and 1. I think if I remember correctly, we actually saw that in the previous section. We also saw that sine of x is actually an odd function. If you remember, for any x, we have sine, excuse me, let me just fix that, sine of -x is equal to negative sine of x. So in other words, the graph is actually symmetric about the origin. That's something we saw near the end of the last section. And as we said already, the sine of x is actually periodic with a period of 2 pi. Okay, so here we have some other properties where the maximum of 1 and the minimum of -1, where they occur. Now, I did reproduce the graph here. Again, this is what I was trying to say before. Once you get outside the interval from 0 to 2 pi, the cycle is just you're going to go through a cycle again. In other words, the graph is just going to repeat itself. And it keeps on going in both directions indefinitely. Okay? All right, now, but really, instead of memorizing this list of where the max occurs and where the min occurs, I mean, I personally cannot do that. But what's nice is we don't have to. It's really enough to know what's happening in the interval from 0 to 2 pi. That's actually why I drew the graph the way I did, changing color in this interval, to emphasize that once you know what's happening in this interval, essentially you're done because the function is 2 pi periodic. So, okay, so the maximum here, for instance, is at pi over 2. So if we just add 2 pi, if we keep on adding 2 pi and keep on subtracting 2 pi, we're going to obtain all x values where the maximum occurs. And that's what we're doing here. And likewise, for the minimum, same idea. 3 pi over 2 is where the minimum occurs. And to get all the others, we just add and subtract 2 pi indefinitely. We keep on doing that to get all locations where the minimum occurs.